I am very happy to announce, last but certainly not least, Sheila Sundaram, who's going to talk about the plethystic inverse of the odd Lie modules.
Thank you. See, I need to share my screen. So let me just, okay, let's hope I can do this. Can everybody see it?
Yep.
Everything? Yes. Okay. Well, first of all, thank you very much for the opportunity to speak, and thank you to the organizers for this wonderful conference and for sticking around for the last talk. And I have to say, it's a little bit daunting to give a talk that's following amazing talks. So I'll do my best to keep your attention. All right. So this is the talk, as you can see, there's the word platistic in there. So what I'd like to do, rather than go into the nitty-gritty details of platistic computation, is give you a broad overview of what you should think about when you see a platistic formula or a platistic identity from the point of view of representation theory. And Georgia's talk yesterday, wonderful talk with lots of things, was actually a great introduction. So let me just start with some background. So the way I'd like you to think about symmetric functions in this talk are as characters of polynomial representations of GLM. They are by Schur-Weil duality, also in correspondence with representations of the symmetric group. And most of the time it's more useful to think about them as GLM representations, but in some cases you do have to think about them as SN representations, and I'll point that out. Okay, so what is plethism? So like I said, I'm not going to tell you how to compute it, but you should think of it as composing GLN characters, going from one module to another. Right? For the symmetric group, it's a little bit messier to describe, so that's why I'm going to try and avoid it, but it corresponds to Riesz products, taking Riesz product representations. And here's a quick overview that probably most people don't need about partitions. So this is my notation for a partition of n. L of lambda is going to be the number of parts of lambda. PR is the rth power sum symmetric function. So it's the sum of each variable raised to the power r. And it extends multiplicatively to basis over Q, rationals, of the ring of symmetric functions. S lambda is the Schur function indexed by lambda. And again, I want to think of the Schur function S lambda in m variables as the GLM irreducible indexed by lambda. It's also the characteristic of the SN irreducible indexed by lambda under the Frobenius map that Georgia mentioned. Okay, so I don't know if you can see this, but there's something blocking the top of my screen. I mean, I know what's there, so I hope it's not blocking you.
We're fine.
Thank you. So the homogeneous symmetric function Hn of degree n, that's the Frobenius characteristic of the trivial representation of Sn. So if you think Farrer's diagrams, it's all boxes in one row. But more importantly, it's also the character of GLV acting on the nth symmetric power of V. And similarly for the elementary symmetric function, it's the Frobenius characteristic of the sign representation, but it's also the GLV character acting on the nth exterior power. And then P1 to the power n, that's the characteristic of the regular representation of Sn. So this will be important because I'm going to be talking about the regular representation a lot. And it's also the character of GLV acting on the nth tensor power. Okay. All right. So I'm going to be looking at series of symmetric functions. So H will be the sum of all the HNs, including 1, and E will be the sum of all the ENs. And just again, this is really what I want you to remember about plethism. If you see something like H plethism with F, it's the GLV character of the symmetric algebra over the GLV module W, where the F's basically encode the characters of the components of W. And similarly, E plethism with F is the GLV character of the exterior algebra of W. And more specifically, you don't really need to pay any attention to this, but you'll see things like H lambda plethism with F, and it's basically the character of this piece of the symmetric algebra, and likewise for E lambda of F. Okay, and the last thing on this slide is the reciprocal of 1 minus P1, which if you expand as a geometric series, that's the GLV character on the full tensor algebra. And here's what it is in terms of the symmetric group, if you're more familiar with that. I'm actually not going to say a whole lot about this. These are wreath product representations, but what you should be paying attention to is the stuff on the left and the stuff on the right of each line. This is how you actually compute the plethism. You compute it as a product of the plethism of H subscript Mi, which is Mi is the degree, and Fi, I is the degree of the symmetric function Fi. So just, for people who've seen this sort of thing before, I'm just putting this up, but I'm not going to say a whole lot about it. The one place where one does have to refer explicitly to the symmetric group is when talking about the involution omega, because it doesn't, it means more in the context of the symmetric group than it does in GLN. So omega is the involution that corresponds to tensoring with the sign representation, and it just sends the homogeneous symmetric function to the elementary symmetric function and extends over the whole algebra of symmetric functions. Okay, the regular representation. So from basic representation theory, this is what happens in the symmetric group. We have this familiar decomposition of the regular representation into irreducibles. The irreducibles correspond to short functions, and they occur with multiplicity. Can you see my cursor when I do that? Sorry, I'm not really, I don't know if you can see that. The F lambda is the degree of the irreducible. So it's the multiplicity of the irreducible representation. Like I said before, there are these different decompositions of the regular representation of the symmetric group that turn out to be fascinating and important and have connections to all kinds of areas of mathematics. And one of them is this fairly simple one, I think. So you can do this for any subgroup of any group. You can take all its irreducibles and induce up to the big group, and it will give you a decomposition of the regular representation of the big group. Where in the case of the symmetric group, when you choose the subgroup to be the cyclic subgroup generated by the long cycle, or if you think in terms of Coxeter groups, this is the Coxeter element, then if you take all the irreducibles of the cyclic group and induce those up to Sn, you get a decomposition of the regular representation that's been studied for a long time. It's still being studied. It has connections. It leads to the study of the co-invariant ring, which is a very active area now, Macdonald polynomials. All that stuff starts right here from this very simple fact. So this is my first decomposition. And the reason I wanted to mention it is because the summands in that decomposition are what are going to let me define Lie subscript n, which was sort of in the title. This is the star representation in this talk. It's what you get when you take a primitive nth root of unity and induce from the cyclic subgroup up to the big group Sn, right? And at the other end, and so if I go back, whoops, sorry. if I go back here, so this is the k equals 1 case is the Lie representation, and the k equals n case is the representation that I'm calling conj sub n, which I know is an awkward sort of thing, but there are too many C's. So this is just a permutation representation, and you're just conjugating, Sn is acting by conjugation on the class of n cycles. Okay, so one of the first instances of an interesting plethism is actually a theorem of Robert Thrall in 1942, although he certainly didn't state it this way. If you take the sum of all the homogeneous symmetric functions, so you're taking all the trivial representations, and you take the plethism of that with all the Lies. Oh, by the way, the reason this is called Lie subscript n is because it's also the representation of the symmetric group on the multilinear component of the free Lie algebra with the Lie bracket. So Thrall's theorem basically gives you this platistic identity, and it's equivalent to this decomposition of the regular representation of Sn. And this is actually how he stated it and proved it. Okay, so I'm actually going to show you how to decode this formula in a very simple case, in the hopes that it'll sort of make everything else make it make more sense. So I'm going to tell you what this says for n equals 3, right? So I'm taking the regular representation of S3. Well, there are 3 partitions of 3, the single row of 3 boxes, then 2 and 1, and then 1, 1, 1. So I'm going to tell you what each one of these is. So it decomposes like this. This first one is Lie 3, which is, that actually happens to be an irreducible here. It's the irreducible indexed by 2 and 1. The second one is a product, and this is the induction product. So it's a column times a single box. And the third one is just the trivial representation. And so if you remember something from Sarah Browner's talk, something like this showed up in her talk. It's not quite the same. But anyway, if you multiply these 2 things, you're basically adding a box to the 1, 1 diagram in all possible ways to get, again, partitions. So you end up getting twice the partition 2, 1 plus 1, 1, 1 plus 3. And this is indeed the regular representation of S3. Right? So in general, I just wanted to do this so that you could make sense of formulas like this a little bit. Okay. All right. So platistic inverses. Well, what does that mean? So we say that symmetric functions f and g are platistic inverses of each other if, when you take the plethism of one with the other, you get P1. P1 functions as the platistic identity. You can take a plethism of P1 with anything and nothing happens. You don't change the character. Right. Okay, so, and again, possibly the first instance of a platistic inverse identity is this formula of Cadogan, Charles Cadogan, I think. And he was from Jamaica, by the way. So he discovered this in the context of, he was doing something with graphs. So this came, the way he stated this is in terms of cycle indicators. And then, you know, when all the algebraic combinatoric stuff started, people realized that you could write it like this as a platistic identity with symmetric functions. But anyway, platistic inverse identities are interesting because they often correspond to acyclic complexes of modules. Right? So in a lot of the work I've done, I'm always, well, when I look for platistic identities, but then I always look for acyclic complexes. Okay, so this slide is kind of it's what I call a meta theorem. I don't really want to go over this because I probably don't have a lot of time. But I want what I want to point out here is that if you have an identity that tells you what H plethism with F is, it's actually equivalent to a whole bunch of other identities. It tells you what E plethism with F is. So remember, H plethism with the F is telling you something about the symmetrization of some GLV module, and E plethism with F is telling you something about the exterior algebra over that module. And then you can also take alternating sums, and all of these things are equivalent. So that the only thing I want you to remember from this is if you have one identity, you can actually get a whole bunch of others. And they all have different meanings, representation theoretically, topologically. They're all often very interesting. Okay, so for instance, Thrall's theorem is actually equivalent to Cadogan's computation of the plethystic inverse. It's also equivalent to this, the plethystic inverse of the Lie representations. And so here's an example of something that has a concrete interpretation on an acyclic complex. It's the acyclic complex on the Orlik-Solomon algebra for the cohomology of the braid arrangement, which again came up in Sarah Browner's talk. So just if you're only interested in symmetric functions, this is telling you what the plethystic inverse of the Lie series is. Okay, let's see. So a couple of years ago, I had a variant of this Lie representation. And one of the reasons it's interesting, so I'm not going to, so the definition is up there, I'll let you read it if you want, but it specializes this new Lie sup 2, Vic Reiner actually dubbed it Lie sup 2, is the Lie representation when n is odd, and it's the conjugation action on the n cycles if n is a power of 2. Right, so it kind of interpolates between the two extremes in the first decomposition that I put up of the regular representation. And what was interesting about this was it gave me a decomposition, another decomposition of the regular representation as a sum of exterior powers of modules. I don't really know how to interpret this concretely at the module level, but it does give you a decomposition. And thanks to that meta theorem that I flashed by you, you get a bunch of inverse badistic identities. And again, the question is, what do they correspond to? Are there acyclic complexes? We don't really know. Okay, so in the title of my talk were the odd Lie modules, so I have to talk about that. So I don't know if this is the first time they appeared, but I'll just put it down here. I'm going to let Jn be the degree n multilinear component of the free Jordan algebra on n generators. So this is another old thing that probably Georgia knows a lot about. I don't know where it came out of. Dave Robbins studied it in his thesis, the famous Robbins from the Mills-Robbins-Rumsey theorem, plane partitions. So instead of the Lie bracket, which has a minus sign here, you make it a plus. So it's a different bracket. And by Schur-Weil duality, you can look at this as an SN module. You can look at the multilinear component with n generators as an SN module. And you can compute its representation. And this is an old theorem that I proved with Rob Calderbank and Phil Hanlon when I was at Michigan. The Frobenius characteristics of these free Jordan algebras satisfy this platistic identity. It's all the H's, but you take a plethism with only the odd Lies. So just to remind you, if you took all the Lies in here, you would get the entire regular representation. That was Thrall's theorem. Okay. So what I want to do next, I'm going towards the main result of this talk, is I want to take the E series and the H series and split them up into odd and even parts and do something possibly a little bit strange. I want to divide them. So I take the odd ones, the odd elementary symmetric functions, and divide by the even ones. The same thing for the homogeneous symmetric functions. Well, it turns out it's not hard to show. These two things are actually exactly the same. I'm sure this was known. I don't know, I just don't know where it is. It's not hard to prove, like I said. But the interesting fact about these is that there's a nice way to describe them in terms of skew Shor functions. So I need to tell you what skew Shor functions are involved. So it's you take the staircase shape and you take away from it another staircase shape that's 2 away. If you took something that was 1 away, you'd get just a disconnected set of boxes, and it's not very interesting. But this is what MacDonald calls a border strip. So I don't know if you can see that it's connected. The skew shape has no 2 by 2 squares. That's no connected 2 by 2 squares. That's the definition of a border strip. And so the theorem is this: if you take the odd elementary symmetric functions and divide by the even ones, you get a nice skew Shor function decomposition like this. It's an alternating sum, and you get a nice generating function. And yes, these are hyperbolic tangents. I got very excited when I saw this, because I teach calculus a lot to high school students. And so then I like to tell them that I used hyperbolic tangents in my serious mathematical work. Okay, the fact about the dimension of the skew modules is easy to see. I think it's the nth Euler number. And you can imagine that there are lots of combinatorial connections here. Okay, so here's the first main result of this talk. This is actually something that was conjectured by Richard Stanley. And it was very exciting for me because I proved it. And it's the first time I've ever proved anything that Richard conjectured and told me about. So here it is. The platistic inverse of the odd Lie characteristics is precisely this quotient of e's, the odd e's divided by the even e's. Okay, so if you remember from previous slides, there were these alternating sum versions of these things. So that's actually where I want to go next. I want to make everything I had before alternating. And again, the same thing is true. These two alternating odd over alternating even quotients are actually the same. So in other words, this is a self-conjugate thing. That's what it's saying. So this has actually been studied before. It's a theorem of Carlitz that this is true. So this is the analog of the result I had previously, but now there are no alternating signs. So you have alternating signs in the quotient, but in the Shor function expansion, this is a true representation. It's what you call Shor positive. And then the generating function is the same, is similar, sorry, not the same. It's actual tangents instead of hyperbolic tangents. Okay, so here is the next theorem. The platistic inverse of the alternating odd Lie modules is the quotient of the alternating odds over evens. And you might think that there's an easy way to get from the non-alternating version to this one, but actually there isn't. I had to do everything all over again. You know, the technical details were different. So, okay, so how am I doing for time? I'm sorry, I forgot to, I meant to start my timer. Do you know how much time I have?
You're the last talk, so I imagine it's okay. I'm not an organizer, but this is Trisha.
Oh, Thank you, Tricia. Thank you. Yeah. All right, let's see. I had a moment of panic that nobody could hear me when nobody said anything.
Yeah. No, you started a bit late, so just go on.
Okay. All right. Did something happen to the sound? Can you hear me?
I can hear you.
Oh, okay, good.
Sorry,
Right.
I stepped away for a minute. Apologize.
It's all right. Okay. So I started with the regular representation, coming from the cyclic subgroup. And then we went to thralls decomposition of the regular representation. If you hit thralls decomposition with omega, you actually get the Eulerian idempotents that were in Sarah Browner's talk. These are the things that lifted to the Whitehouse modules. Sarah Whitehouse lifted them to Sn+1. But these Eulerian idempotents were originally defined by Gerstenhaber and Schack, or Schack, I'm not sure how to say that. And Phil Hanlon proved that the representation was given by this expression. So it has to do with Hochschild homology and the Hodge decomposition and things like that. Okay, then there was the, there was the variant of Lie that I mentioned, which also gives you, again, 2 decompositions of the regular representation. And the last thing I want to end with is what I think is a new decomposition of the regular representation that comes from these odd Lie modules. And it actually comes from that platistic inverse calculation from Richard's conjecture. It says that the regular representation decomposes like this. It's a plathism where you take the sum of all the hooks and the inside part is all the odd Lies. Okay, so this is it's a very strange thing that I certainly have never seen before, and I would love to hear if anybody else has, if you know, if you've seen it in any context. And I think that's all I have. So I want to thank the organizers again and wish the AWM a happy 50th birthday. Thank you very much.
Jim.
Thank you, Sheila. And are there any questions?
Yeah. Hi, nice. Nice talk. Thank you. I'm wondering if you tried in that those analogous formulas with tangent and hyperbolic tangent. If you tried, what happens if you replace each xk with I xk?
Yeah, actually, yeah, that is how they are related. Let's see, where'd they go? Yeah, so if you replace I here, then you will get, this will all translate, all the minus signs will become pluses, and here you will get a power of -1, right? To get the actual platistic inverse is a little trickier, because when you introduce minus signs in the inner factor of the plathism, literally all hell breaks loose. You have to be very careful. It's composition, right? So if you know about species and things like that, you have to be very careful when you start putting in minus signs. So yeah. Thank you for asking.
Any other questions?
Yeah, I have a question. Or Franco, you can go first.
Oh,
no, I insist you go first.
Okay. I really like that talk. Thank you. I guess I'm wondering, so you have all these decompositions of the regular representation, and like in one of the cases you had the Eulerian idempotents or representations, which have this topological interpretation. Is there do you have topological interpretations or conjectures for like these other decompositions?
No, I would love to know. It's something I've been thinking about for 3 years now. I've been looking and I don't know. Yeah, so the first thralls decomposition, by the way, is also basically it's a restatement of the Poincaré-Birkhoff-Witt theorem, right? It says that the enveloping algebra of the free Lie algebra is the, oops, sorry, didn't mean to do that. I should stop touching this. Is the, where was it? The enveloping algebra of the free Lie algebra is the full tensor algebra. Like, that's what it's saying at the level of GLV modules. Okay. So yeah, I don't know of an interpretation. So there were platistic inverse identities. Again, I'm sure there's an acyclic complex somewhere, but I don't know. Yeah. Thanks.
Thanks.